Welcome, everyone. For today's prep, we're going to start to look at how to find the absolute extreme points for our functions. And for today's prep, we're just going to look at the definition and just try a couple graphical examples. All right, so let's start with the definition. What is the absolute maximum of our function? And before we get to this, we're going to first look at the local maximum, kind of more of what we're used to. So kind of have the two definitions here so we can kind of compare and contrast. So a local maximum, well, we say a number x equals c, and we classify this as a local maximum of our function f if, when we take that number x equals c and we plug it into the function value we get is bigger than all of the kind of surrounding function values. So for x near c. All right, so how to kind of picture this local maximum? And the way to kind of picture this is we want to draw just a little circle around our point that we think might be a maximum. And what we're doing is we're checking if we look at just the section of our graph that's inside that circle, is our point kind of bigger than all of, or is it higher than all of the surrounding points? So let's look at one example here. Let's look at this first graph. All right, so a local maximum is just a high point on our graph. It's kind of like a mountain peak. So let's look at this first graph. And we've got this function. It's going from endpoint to endpoint. And when we look at this, we kind of see two high points on this graph. So I would say this point right here and this point right here. Those are kind of like the two maximums. Now, why are they local maximums? Well, let's imagine drawing a little circle around each of those points. So let's put a little circle here and a little circle here. All right. Now, let's look at just the section of our graph inside each of those circles and compare it to the point we're thinking is a local max. So let's start with this one. That's the point we're interested in. And let's compare it to all of the other kind of surrounding points that are on our graph that are just inside that circle. So if we compare it to all these other little points, well, yeah, that point is higher up. The y-coordinate is bigger than the y-coordinate for all of the surrounding points that are in that little circle. So we would consider this a local max. Or sometimes we say relative max, same thing. Same deal over here. So if we're thinking this is a if we're thinking this is a local max, if we compare it to all of the surrounding points that are inside this circle, well, yeah, all those other points on our graph that are inside the circle are lower than that point. So this would also be considered a local max. Okay. So local maxes, we're just looking at a little surrounding section of our curve. Now an absolute max, same idea. We would consider a number x equals c to be classified as an absolute maximum for our function if when we take that number, we plug it in, and the function value we get is bigger than all of the entire function values, where we're not just restricting ourselves to just a little circle anymore, we're looking over the entire domain of f. So we're really looking at the entire graph. So a local maximum is like a mountain peak. An absolute maximum is like the biggest mountain peak. It's the Mount Everest of mountain peaks. All right, so let's go back to our graph here and let's try to figure out where our absolute maximum is going to happen. And when we do this, we want to look over the entire graph. So let's start with that same point, that point at 2, 5. Now it is a local max because in this little section here, it's the highest point. So it is a little mountain peak there. But if we scan through the entire graph, I eventually, once I get over to here, all these points here are actually taller. They're higher than it. So this is not an absolute max because if I make it way over here, I have points that are kind of bigger. But this point is an absolute max because if I scan through the entire graph, no other point is going to be that tall. So this is going to be an absolute max as well. And if you have 2 points that are the same height, well, then you have 2 places where the absolute max happens. So if you had 2 Mount Everests that got to the exact same height, well, then would both be considered the absolute max. But in this case, this point is not the same height. It's a little bit lower. All right, so we have 2 local maxes, and we have an absolute max over here. Now, the definition for local minimum and absolute minimum, very similar. So I don't have those listed here, but similar definitions for absolute min. So the only thing different is it'll be less than or equal to. So local min is a low point on your graph. Absolute min is the lowest point on your graph. So let's do the same thing. And let's think about local mins. And I want to label this point. This is 1, 4. All right, so what would be, let's scan through. And for a local min, we want to look for low points on our graph. So looking at this one, I see kind of 2 such points. And I see this point here and this point here. So again, let's kind of go through, figure out what's going on. And for local min, we want to do the same thing. We want to imagine drawing a little circle. So let's draw a circle around each of those points. And if it's a local min, if we look at just the points that are inside that circle on our graph, well, then our point should be the lowest spot. So let's start with this point here. So if we look at all the other points inside that circle, yep, that's as low as it gets inside that little section. So this would be a local min. Or if you want, relative min, same thing. Okay, well, let's go to the other one, this other point. So if I look at all the points on my graph that are just inside that little circle, this one point is the lowest of those. So all the other little points are a little bit uphill. So this would also be considered a local min. All right. So what about an absolute min? Well, this is going to be the lowest spot on our graph. And if we're looking, when we think about absolute, we want to scan through not just a little section of our curve, we want to scan through the entire thing. So we want to look at the entire graph. So let's start with our endpoint here. And yeah, in this little section, it's the lowest spot. But if I scan through the entire graph, eventually I hit a whole bunch of other points that are lower on the page. So this is not an absolute min. But if I look at this point here and I compare it, I scan in both directions, well, yeah, that one is the lowest our graph ever gets. Any other point that I pick anywhere is higher up on the page than this point right here. So we would consider this an absolute min. Okay. So let's write out. So sometimes when we're going to be finding or answering questions, we want to know what the absolute max value is. So if we kind of formally write our conclusion here, what we found on this graph is that the absolute max value is equal to, what did we find for the absolute max? Well, we found the point where it happens. What's the value of our function there? So the absolute max value is the y-coordinate. So it's equal to 6. And this occurs, or this happens, at x equals 8. So you want to think of the x-coordinate as kind of like the location, and then the y-coordinate is the actual value of the function. So same thing for the absolute min. So where did we find, what point was the absolute min? Well, it was this point right here. So what's the absolute min value? It's the y-coordinate. So 1. And we found that this happens at x equals 6. All right. So where we're going with this is this function's kind of special because it's a continuous function, so there's no jumps or breaks in it, and we're going from endpoint to endpoint. So we only have a excuse me, a closed section of our graph. We're looking at a closed interval. Ooh, I think we'll end it there. So in class, we're going to consider these other examples, and this is setting us up for something called the closed interval method and the extreme value theorem. So if we're going to be dealing with a continuous function, and we're only going to be looking at a kind of a closed interval, so we're going from endpoint to endpoint, then our function is going to be guaranteed to have both an absolute max value and an absolute min value. And that's precisely what we saw here. So this function is continuous, so there's no jumps or breaks, and we're going from endpoint to endpoint. So, and that's exactly what we found. We found both an absolute max and an absolute min. And these other graphs, things are going to go wrong. So in these other two graphs, they're not necessarily going to have an absolute max or an absolute min. They might have some, but not all. So we'll check that out in class. So we'll see you then. Bye-bye.